I'm going to show you two problems here. In particular, it's going to be number 50 and 52, which are just classic problems that involve wires bent around points of observation. So in this case here, I have a wire sort of bent in this weird straight arc in this straight loop here, and some current I has been sent through the wire here. And the question is asking me, what would the magnetic field be at that point in question right there? So in fact, in this case here, there we go. Okay, so we're just going to get started on this problem here. So what is the magnetic field at this point right here? B is equal to what? Okay. Now you look at it very carefully, it's like it will be a superposition problem. So the B field at this point will be the B field due to this wire segment, plus due to this bent wire, plus due to this wire segment. But it's a classic problem, and I hope you can quickly recognize a few things. In particular here, as the current flows in this wire here, there's a couple of things. One is no matter what magnetic field is producing here, the current here, or the charge flow, you can call it V if you want here, is sort of along the same axis as it would take to reach the point in the first place here. So this is sort of like your R vector right here. So at any given point on the wire, this is the direction you have to take to get to the field point. So in other words, for this wire right here, V is parallel to R, and you know that Biot and Savart law has a magnetic field in there that B is proportional to the sine of the angle between V and R. So if V is parallel to R, then you could say that the angle between them is 0, and the sine of 0 is 0, so the B to this wire segment down here is 0. This wire, in other words, contributes nothing to the magnetic field at this point. Another way you can think about it is you can think about it like a straight piece of wire, and you know from the right-hand rule that if you put your thumb in the direction of current and spin around the wire here, this wire here is going to have these magnetic field lines sort of circulating around it like that. Now these circles come out of the screen and into the screen. I'm trying to draw a 3D picture on a 2D surface, which never works. So these would be nice and thick as they come in front of the wire like that, and they're sort of thinner as they go out. But the wire ends abruptly there. So there is no contribution of this wire at this point. So you either get it from some geometrical considerations of the Biot-Savart law that the point of interest is parallel to the current right there, and so the sine of 0 is 0 is 0, or the fact the wire ends right there so it can't contribute any magnetic field. Now in reality there might be some fringing field coming off the edge of the wire that might contribute a little bit, but it won't be very much. We'll ignore it for this problem. And the funny thing about this problem is everything I just said about that wire actually pertains to this one as well. Because in this wire here, okay, the current's going up and out like that, it's leaving the system here, but the observation point from any one of these segments of current back down to this point right here is still R like that. So in this case here, yeah, R might be pointing down to the right, I is up and to the left. Either way, the angle between I or V, which is the movement of the charge in there, and R is sort of anti-parallel right now. So anti-parallel, it was parallel down here and anti-parallel down there. Either way, you get a 180-degree angle, and the sine of 180 is equal to 0. So once again, this wire won't contribute anything to this magnetic field at this point for the same reason as this one right here. Either the geometry of the Biot-Savart law or the fact that these circles which are going down this wire, going around this wire here, according to the right-hand rule, magnetic field circulating around wires, just doesn't, the wire ends right here. It doesn't contribute anything further back past this edge right here where the wire sort of ends right there. Nothing gets contributed past that. Once again, in reality, maybe there's a bit of fringing field in here, but in practice, nothing's going to be there. So, no contribution here, no contribution here. What are you left with? The circular arc now. We do have a result for a circular arc. If you look in your book, or it was done in class, the magnetic field due to a full arc is done. You can sort of integrate along this curve here. You can break these points up into segments here. And for this particular case here, the current is always this way, current I like that. And that's always going to be at a perpendicular angle to R, which is the point how you travel from the current segment down to the point of observation in question. It's always a 90-degree angle. So in this case here, the Biot-Savart law, you'll always have a sine of 90, which is equal to 1. So the Biot-Savart law is not going to be 0 in that case here, but you'll get a nice integrable expression which is not going to be 0. You'll get some contribution to it. So I'll leave it up to you then to set the Biot-Savart, but you'll get something like this. B is going to be equal to the integral from 0 to pi to 0 to some theta, which I believe is where the arc exists in there, of all your other business in here that involves the R times the ds and the R squared in the bottom, and the sine theta has just been dropped out to be 0, and all that sort of thing is going to go in there. And from this, you can get that the magnetic field contribution to that point is going to be some nice non-zero expression there, but it just will be that arc that contributes to the overall magnetic field. So I'll leave that one like that.